Hello, everybody. Hope y'all had a good weekend. Some nice weather. That seemed a pleasant change after the sudden cold snap after it got nice the first time. But back to computer stuff. We're sitting in enclosed rooms, like the lab I'm in here, where not a window in sight, just a whole bunch of computers everywhere. Typical sort of place where a software developer would work. We've got a few things to go over. Last few classes, we've been talking about writing files, persistent data, seeing some of our options, in particular, the standards that kind of extend beyond any particular programming language, XML format or JSON format, immensely popular. Looked at SQLite to have the advantages of a relational database in the software we write, and just things to kind of keep stuff around. Just two other things I want to look at before we move on from writing files, and then some stuff about recursion this evening. One of them is, well, kind of goes along with writing files. All our examples, to strip them down, make them nice, straightforward things for the class examples, without a lot of clutter there. We just wrote the file right to where it was. But sometimes we might need to work with files that are just somewhere on the hard drive. We might not know where they are, how to have to go out and look for them, and how we deal with all the operating system stuff where our software is running. So a couple things about that. And I also wanted to do an example that related to the try except blocks, exception handling. I believe everybody would have seen that in the prerequisites of this course, where we can deal with certain exceptions, and textbooks and tutorials kind of follow suit, because tutorials tend to be very short things. Always fall a little short on that. The standard example for, well, we're in Python, so when we put together that try except block to catch any errors that might happen, the standard example is to output a string, just output a message. Okay. If we don't do any exception handling, the Python interpreter outputs a message. So nothing changes there. We didn't really fix the problem or deal with the problem. So I'm going to do a small example of going through something that actually fixes a problem. And I had something in mind with files for that. And then we will jump into recursion. Just a couple points there. So that's what's on tap for tonight. I guess we can start by looking at the stuff for, because with what we were looking at the past few days, we were writing files, but where do we put them? How do we find them if we forget where we put them? That sort of thing. So I'm just going to jump in and do this with an example. Like everything else we've been looking at, there's some libraries built in to work with to do this, to use for this. Open up Spider. When this class started, I had the intention of using a bunch of different IDEs. It seems like I keep going back to my preferred one. There are a lot of advantages to this one, and Python wasn't an afterthought in Spider. That was why they put it together. Python's usually an afterthought that's just added on to an IDE that was kind of designed for something else. But with Spider, the reason I like this for Python is when they sat down to design it from the beginning, they intended for it to be used with Python, because Python's always an afterthought. So they went one that was explicit specifically for Python. So it has a couple advantages. But in general, it's just an IDE that I'm fairly happy with. So there's a library we can use to work with our stuff. You may have encountered this somewhere before. We want to import the OS library, which actually, there's two libraries I want to use. And I almost always use the OS one this way. And I'll say import all, because there's like two of them. If you remember, I believe we've mentioned it before, when we import things, that's really a directory structure where we're used to doing that as a string with slashes, but we can also treat it as an object. This is the library that has the tools to treat our entire directory structure on the computer we're running our software on as an object. Kind of like why the dot operator here is here instead of a string with a slash in it. The OS and OS.path are the two that have most of the tools we need to work with. Oops, that's not how to spell from. There we go, spelled word correctly. So I typically do this, and I even took a few minutes today to look up the handful of things I'm going to use so you can see which ones come from which one. When we go to run this, like if we put this in an object and compiled it, that asterisk would be replaced by anything we actually use. So whether we say import everything with the wildcard selector or give it an explicit list, by the time it actually runs on the machine, those are equivalent. Usually I do the star, and I've been doing that for years, just import everything from both libraries. And today, as I was getting ready, I was like, well, maybe I could take a few minutes and look and see which one of these methods are in which thing. And when you see the names, you'll realize what they're for pretty quick. So the OS library, short for, the access to our operating system, has things like make directories, so we can make new folders. Remove directories, so we can do those. Or list directory, which is very, very important so that we can get all the directories in a certain place on the storage, the hierarchical structure there, as a list, so then we can start looking through it and stuff. Which was basically what our first example here was going to be. And the OS.path has some things, in particular, things to check with. Is there, which you can probably guess from the name what that does, and put that in our condition. If the thing we're currently looking through when we use the list directory and turn everything in, like go into a certain folder on our computer hard drive and look at everything in there, we can do that condition to check and see if the thing we're currently looking at is a directory. Same thing for files, is file. And then I decided to throw in this other one because it's good form. We also have this method join, which is a special type of concatenation for directory paths. Let me just print something with it real quick. So maybe we have S1 is the first part of a directory, right? The C : I'm gonna leave off the slash. Then S2 is users folder. We'll probably want that. And I'll just print join S1 with S2. And throw a slash in there. Maybe I didn't, oops. Maybe I didn't need to put the slash here. There you go. So you can see it's a special type of concatenation operator that puts together file paths. So we can build up path names. So it's good form. The main thing is it does it specific for the system. So normally it would on a Windows machine, it would add in a couple things. Let me go ahead all the way into something. Maybe I didn't realize it was. Let's see if this does the same thing. I need to say that again. Okay, there we go. It threw the slash in there that time. I don't know why it did the first time. But we're on a Windows system, so we should be using backslash for our directory. Obviously, that was adjusted many decades ago, so that we can use either one on the Windows system, but that's appropriate for the system. So if I jump over to the Chromebooks pulled out today and ran that same code on the Chromebook, which is a Linux system, it would use the join would automatically go in the / to calculate things together. I'm not sure why it didn't do it the first time, but that's one that's good form for when we're working with directory structures. So then we can generalize our code and we don't have to worry about whether we put the / or backslashes. And that method will have Python do it, so it will be appropriate for the system we're on. I just thought I'd throw that in there because that can be a useful thing. Oops. Excuse me. For one. This rain seems to be having me cough more than normal today. I guess I should apologize for that now. The wet weather. I woke up this morning, and after I went outside at lunchtime around 2 o'clock and came back in, the wet weather seems to have me coughing much more than normal, which I always cough a lot. So sorry about that in advance. It's been going on for like 4 hours now. So hopefully maybe it'll clear up in a few minutes, but I have a feeling it won't. So the example I wanted to kind of work through here is just, we'll just look at one of the directories and get started with a simple example on how to use these. So I'll set up that same one. Whoops. So if you're following along, your file path might look a little bit different. Documents, I'll use that. So that's the general path we want to look at. And well, you don't know what a documents folder is on the PC. We have a whole bunch of things there. A whole bunch of folders filled with other files. I should probably put something in the delete folders. There's something in here. Maybe a new text file. Hello world. That'll relate to something in a moment, but just something. Our normal directory structures, the folders and files we stick in them to keep them organized. So start with the documents one, and then we can use this list directory method to look through that. So for, I'll say folder. Obviously, the technical term is going to be directory. So you can kind of see from those imported libraries that Python uses directory. So when I was getting this lecture ready, I decided to use folder here to help identify easily what is reference names and which ones come from the library. So for all the folders, oops. For all the folders in, we want to say list directory of that path. So the thing's stored. What did I turn around? That's weird. So that little file path there points to a folder. So we can walk all the way through that now and just sort of check what we have. I guess we can check if it's a directory. I'll use that join method here. Join, I'll do it without that. Show you what goes on. Let me build up to this. So that normal thing I like to do is showing the error so we know how to spot it so we can fix it. So if the thing we're looking at is a directory, we'll print the name of it. And then we'll look inside it. Yeah, for F in folder, print F. So also, this is going to throw an error message, which I'm going to talk about here in a second. I guess I could save this somewhere. So I'll go ahead and save this. Delete folder will work. Well, it's this directories. .py. So just gotta give it an arbitrary name. So should be able to loop through that whole thing. And if we're looking at a folder, print out the name of the folder and then look inside of it, which is going to give us an error message. Another 2 errors here that we'll come back and fix. So that looks kind of strange. Just gave us a bunch of slashes. That's not what's in the document folder. And sort of a question is, what are those slashes referring to? And that's because where's our print statement? So that hit true somewhere and it printed it out, but it didn't quite look at the right thing. So it was looking at something, but maybe a picture would help here. I'll start on screen. So we have that file path. That's supposed to be the file path. And then we're going to loop through it. We're going to loop through everything in there, which is a bunch of other folders. So we'll add a slash and then look at something else. So that's what we're checking here. We're just checking this thing that we added afterwards. So when we say to print that, well, it kind of already lost track of it. So it only printed that slash that came right before it. It's like, oh, I saw something. And there was a slash and there was a folder. So it got a little confused. So what we need to do when we check things like that is we need sort of the whole file path to it. So that's where that join method comes in handy. Or you could type the whole file path if you wanted to. It's just generally better form to do it this way. It generalizes your code, sort of puts all the file paths into variables. So then you can retrieve your starting point from the operating system and build them up from scratch. And as a programmer, you don't have to know what they are when you put your code together. You're going to generally ask the computer what these are. So we want to join path with folder and then check and see if that's a directory. Oh, why is this not working? Is this my turn? All right, sorry, I got off somewhere and I have to figure out, oh. I see what I did. Hopefully y'all noticed that if you're following along. I imported that library. I already talked about the one the module we imported. Then the method we actually want is list directory. Let me try this now. I'll go back to that first error message I went through. So from there, it looks like it didn't find any folders. So really, this is that picture I was drawing a second ago. Sorry, I left off part of that metadata. We didn't want a list. That actually casts something into a list, which is kind of the useless thing to do with a file path, because that's a string, so it already is an iterable list or a tuple in Python. But we put list directory, we find a bunch of folders, and we're checking to see if they are, but it says they're not. And oh, I can come right over here and look at my documents folder and see that there should be a bunch of folders in there. So whenever we loop through, we need to join that with our original path, because then we have that full file path, not just the little part we tacked on at the end, if that makes sense. I'll draw a little picture. So we have our the file path that we're looping through there in our directory structure, and we check each item one at a time. So if that next thing's a folder, before we were only looking at this. So, and that, as far as the file path, if all the stuff before that was gone, that last little part is just a string, which isn't a file, which isn't a folder. But when we join it together into the full absolute address of that folder, then we should be able to recognize it as a folder. That's one of the most common mistakes to make there, to forget that when we loop through that and we run the is directory on the thing, the individual item from that list we're iterating through, that's only the string that goes at the very end of the file path. So we need that whole file path. That's one of the easiest mistakes to make there. Another thing you have to watch out for, and the reason I decided I want to do the try catch stuff this evening. Oh, point it right here. These files, the my music, my pictures, my videos, those are the ones that Microsoft put on my machine, right? Those just come on every version of Windows. They're built in there. And there's a new thing. I don't remember this happening on Windows 11, but if I come up to say the My Music folder and hit delete, you'll notice nothing happens. Microsoft won't let me delete that folder. I'm pretty sure I used to delete them on Windows 10 all the time. I would delete them and then recreate them if I forgot to change where the camera saved to or something. But it's not letting me delete them. And there's another error if we try to do something like this. So if we have a directory, that means there's another thing we could walk through. So if we nest a loop in here, so if we have a directory, we'll print out the name of it. And then, so for F in, again, list directory, not list like I did the first time, sorry about that. But again, we need that whole thing. So we'll call the join method on our base path, the base part of our file addressing of things we're going to check. This, the whole point of doing stuff like this is probably going to check a lot. So you usually have like that base file path directory where your starting point, and you'll need to add other parts to it. So we'll loop through the rest of that. And I'll just print I'll just indent it a few times. Oh, actually, I'll do this. That's really good. To show that what that gives us back is a string. We'll say this error. So I did not encounter that prior to Windows 11 because I've always deleted those folders. The ones that came on there, my music, my pictures, my videos. But we can't delete them, and apparently our scripts do not have access to them. I was not happy when I discovered that about Windows 11. So that's something I definitely dislike about Windows 11. But I did very quickly figure out a way to ignore the problem. So this is the first look of the try and accept ones. So I assume everybody has seen this before, our exception handling. We have two types of things, errors and exceptions. Exceptions are small hiccups, just little issues that aren't ideal. Usually things that we can work around, but the computer's not intelligent. It can't work around it on itself. It needs us to tell us how to. Errors are big issues from which there is no recovery. There's nothing we can do about errors. Those are complete breakdowns beyond our control, but those little hiccups we can do something with. I like the boat analogy. An exception is like the boat's things are getting damp on a boat. A little leak, like a small leak in a boat where we could just lay down some towels and we're good for a day or two. It's like, of course it's a boat. There's going to be some water get into a boat. That's obvious. So we can deal with it quite easily. If we're on a boat, we probably have towels with us anyway. An error is like the boat hit an iceberg and is going down quickly. There's no recovery from that. The exceptions we can handle from. And the default we always see in textbooks and then tutorials to try to keep it short is they'll print a message. And they'll be like, okay, if that happens, we'll just say an error happened. I'll write the right word. An exception happened. Probably something more detailed than this, but if we look at what happened when there was no exception handling, the computer printed out a message. So that's not fixing the problem. That's not really doing anything about it. In this case, that's a new problem. I have not encountered that until Windows 11. The Python doesn't have access to my music, my pictures. A Python script does not have access to those 3 folders. And on Windows 11, we cannot delete them. So that's a new problem to me. I haven't had time to think through a good solution. So my at least temporary fix is I'm going to ignore it. I don't use those folders anyway. I don't know why they're there. I usually delete them off my computers. But apparently with Windows 11, we can't delete those 3 folders. And programming languages don't have access, scripts don't have access to them. So that's kind of a headache. So I haven't spent a lot of time thinking about it. My first thought is, well, I'm just going to ignore this. Try to read what's in the folder. Look through this directory. Check everything. If we have a folder, print out the name of the folder. Then go in and look through that folder and add some indenting in the name of the thing inside of that folder. You can see we can keep nesting that. And in most situations, we would probably want to keep nesting that. So that's like a fix. It ran. I know those are Microsoft controlled folders, so I'm pretty certain that anything I would be doing in a script wouldn't involve those folders. That problem's new to me, so for now, my solution is to ignore it. Try to do some stuff, and if not, just try to just ignore it and move on and do some other stuff. We can see that gives us a way to retrieve the folders and the things inside of it. So delete has these 2 files in it. Those folders, it printed out the name, but then it couldn't get access to do anything. So I just jumped in that accept block, and the problems actually helped. Worked around. Ignoring it is a workaround, because sometimes things happen, but the end user would not see an error message, and that is the key point. That's the thing I most dislike about those examples for exception handling. That should be one of our primary rules in programming: is never, ever, ever let your end user see an error message. it's gonna make the end user panic and distrust your software and maybe never even run it again. So that's sort of our goal with whenever we do exception handling, is to completely avoid those. I have another example for using that here in a moment where we actually fix a problem. But yeah, ignoring the problem, analyze it and make sure it's okay to ignore the problem. Something like those 3 folders that Microsoft won't give our scripts access to, which is apparently a new thing. I had not heard of anything about that until I encountered it earlier this afternoon. Was that today? Yeah, that was this morning. So I wasn't quite sure what to do about that. So I'm just good. Ignoring the problem is a good workaround. But notice how this is sort of, it looks like it's leading to a repeated structure. Because there in the printout, that libraries folder, libraries inside Arduino, well, that's another folder. So really I should be looping through that. Where is that? Not much in there, but it's another folder. So that's something that would really need to happen again. So we can set up a loop, but frankly, loops on things like this are a little bit tricky. And I've just found over the years that recursion, it does work a lot better for this particular case, where we're looping through our directory structures. So that's one of our main things for tonight. Just to quickly do something, I'm gonna use that make directories and remove directories. So if we're in a folder, we can check and see which one we're at too, right? So like if folder is equal to delete, we can see right down here, we printed out the result of list directory directly into a string concatenated in. Pretty sure at this point everybody has seen the error message Python gives us if we weren't allowed to concatenate that, right? If we had anything other than a string, we'd say cannot concatenate type and string. You can only concatenate string and string. Pretty sure everybody's seen that message time or two by now, right? So it does give us a string. We can correct that there, so we can check and see which one we're in. And I'll just make some directories over there. So if we are makers, and there's a couple parameters there, but really we just need a name for it. I'll call it test1. I'll make a couple of them. Makers test2. Makers, call it test3. And then afterwards, if you wanted to put a file in that, you already know what to do, right? Because then putting a file in it, that's opening a handler and writing a file to that location. Or if we wanted to copy a file, that's what we would do. Maybe we should do that. I'll do that after this one. So I'll create those 3 folders, and then just for an example of removing stuff, I'll delete one of them. So I'll just copy all this, paste that down. Don't need the print statements. Don't need to keep walking through. I'll delete number 1. That's probably the easiest thing to modify here. So instead of make dirs, we have rm dir, which I'm guessing everybody in here is at 200 level course. You've been studying IT at college level for a year at least, so I'm sure you've seen that somewhere. The traditional remove directory, delete a folder, which would have the same restrictions if we did that in command prompt, in our command prompt, or PowerShell, or Bash shell. Whatever we're using to actually control our operating system. The remove directory, we hit problems if that's not empty. So we have that same restriction when we do it here. And looking from the printout, you can see that list in the delete folder is a little bit longer now, at least when we printed it. But then after we printed it, we went through and deleted something. So if I go over to the actual folders, you all know what happened. That test one file folder got deleted. I'll go ahead and delete those. I don't think I need them sticking around. I'm just going to comment those out. Whoops. Wrong button. Control 1 comments things here. I'll look through here. So if it is theirs, maybe we want to make a copy of everything in that folder. In which case we would just open a file handler and copy it. So for file in list directory, again, join the path we're on with the folder we're currently looking at, then we can just open a file handler and read in the files and make copies of them. With open file for reading as from file. I just trying to put that in. S1 is a blank string. S1 is from file read. I have a few lines for line in from file. All this we've seen before, right? I'm gonna make a slight adjustment here in just a second. S1 equals line, whoops. I can just put a line there again. Got a little distracted for a second, forgot what I was typing. So we can just loop through, read all that stuff in with open file plus underscore B2. Yeah, that'll kind of work. There's a slight problem with that. I just want to get the at least general idea of it. To file, and say to file dot write, whatever's in that string. So write the whole thing. Hopefully that makes sense. Make a copy of it. Or if it's a text file, which I think there's a text file in there. Actually, the only two things in there are text files. I should probably put something in this text file so we can see that that's going to work. The reason I had that one was to see the correcting something with the try except. Actually fixing a problem instead of just, well, repeating what would happen if we didn't fix it at all, which print out an error message. So we'll just read in all the files and make a copy of them. Works fine for the two files in there right now, right? A Python script, that's just a text file. And the other one is explicitly a text file. They're both just text files. But if I went over here and created, say, bitmap image. That one might be a bit of a problem to just read and write. But we did see something last week. We did see that W and R aren't our only options. We can also read binary and write binary. So then it doesn't matter what that file is, we're just gonna read in the binary code from it and write the binary code right back into the file. So basically make a copy. I almost forgot. Join. I'm just gonna build the string. So we have the path thing plus the folder thing plus the file. We need that full directory. We'd have to nest the join method more than once. It wasn't in my original plan, and then I thought, oh, I should show that because that's considered good form. I almost never do it. I just build up the directories and just use a // like we need on the Linux or Mac system. And Windows will work with it. What I normally do, but there's different options. The join method's a little bit better. I think I got so no error messages. Wait, why didn't that? Oh. Well, that's putting in an error. I'm not sure where that error message is coming from. I didn't actually prepare this line. This one just popped in my head. Like maybe we should look at how to copy and paste files. I'm going to comment that out and we'll come back to it if there's more time. But the basic idea there is we'll come back and look at that if we don't run out of time tonight. That one just suddenly popped in my mind. So it was sort of drifting away from our plan for today. But the basic idea is that, oh, I guess I can comment all this out again. Comment all that out. If we want to make a copy, we manually just read it in and spit it back out. I haven't set up error messages and stuff. I didn't really prepare that part and just suddenly realized like, oh, I should show that. There we go. Now we can at least see the stuff in there. And the key point is read them in and write them back out. And if you do read binary and write binary, it should all it should work for any file because all of our files are binary files. We'll come back to that one if we have time here in a little while. There's a bunch of stuff, so I shouldn't get distracted on something that was suddenly a side thought. But copy and paste have to be done manually. Is the main thing there. And yeah, without getting rid of that try except block, it's kind of hard to figure out what the error is. So we'll come back to that if there's time. But notice how we do the same thing. We look and see if it's a directory, and if it is, we loop through this thing we know is a directory. Look to see if it is a directory, and if it is, we loop through it. So you can see that's a repeating pattern. We could set up a loop to do it. The end condition on the loop gets a little odd. It's not too bad, but over the years I found that is something that works much better with recursion. That was the main points I wanted to talk about with those, that we have those, the ability to work with our directories. We can go through search them once we bring those in, read the files that are there, look for different things. A very useful tool, but an easy thing to get lost in. And well, like that idea I suddenly have. If we don't run out of time tonight, we'll come back and fix that. But like I'm saying, the loop here can be a little tricky to get the end condition right in those loops. Without just making your loop while true and then putting that in a try catch block, so you just move on whenever it throws an error message, which can move on at the wrong spot anyway when we do it that way. And over the years, I found this is a nice little structure to put into a recursive call, as opposed to a loop, which is the next thing to talk about. And one of the main ones. Really, that one I just wanted to make sure and point it out. So we just spent 3 days talking about writing files. So we should probably at least I figure we should at least take a quick look at the working with directories so that we can write files in good places. Normally, we're not going to want to write files in the same spot as our software. Well, normally we can't write files in the same spot as our software, right? On all of our systems, Windows, Linux, Mac, the default installation place is probably like program files or program files x86 on a Windows machine, or one of the bin folders up at the top level on a Linux machine, or a Unix structure. So that would include Linux and Mac. But those folders where we don't have write access. So then we normally install our software there so that it can't accidentally get changed, but that prevents us from writing files in the same place where the software is installed. So we might need to go out and work with the operating system as well. If you start playing around with those methods, you'll figure some stuff out pretty quick. Try the while loop. It's not bad, but it's a changing condition. We can't just look for a number. We have to look for the results of other conditions. In a sense, what you have to end up doing, I'll put it in the form of a while loop, as far as continually nesting those for loops to walk through directory structures. Essentially, you have to check another condition, if that makes sense. And then like nesting if statements inside of that. 3D, yeah. So to really be able to catch every situation, it's a really odd condition to put in a loop, which defeats the entire purpose of a loop. A loop isn't something the machine does on its own. And that leads into our next structure. It's an interesting thought experiment if you want to figure out what that is, but you basically end up having to nest 3 loops, which looks a lot cleaner if they go down at the bottom of your while loop, obviously, and just check that. And then the value that you get from those is what goes there. I knew I was getting ready to erase that, but a good little thought experiment, but it makes the loop really hard, which completely defeats the purpose of the loop, because loops are just there to be easy, because what machines actually are capable of doing on their own can be really difficult for a human. At times, downright impossible. So recursion is controlled feedback. Controlled feedback to repeat instructions. Instruction calls. I'll spell it out like that. That's exactly what it is. As Americans, that second word in that little thing I wrote up there probably catches our attention, because we have a very specific case of that in mind. Okay, we've all encountered audio feedback, I think, right? Somebody like maybe sings into a microphone, sound goes down a wire, gets amplified. So they sing into the microphone, sound goes down the wire, gets amplified, comes out a little bit louder. And if things are in the right position, that sound's going to go back in the microphone, go down the wire, get amplified, come out a little louder, go back in the microphone because it's moving at the speed of sound and electricity. So far, far quicker than a human could react to. It's going to keep going around there. And before long, the room is just filled with an annoying sound, right? We're all quite familiar with this. If I go turn on my audio here. Turn on my audio here. Let me turn that back off. But I think everybody's familiar with what audio feedback is. The output becomes an input. Usually an annoyance, kind of like what I just did with the Zoom call, right? We hear those all the time. The output from the speakers becomes the new input for the microphone, and it just gets stuck in a loop. Often an annoyance, but quite a few musicians have learned to work with that feedback. They learn, guitarists tend to do it a lot because they have an instrument that produces high-pitched sounds anyway, so they can grab those they figure out where to stand and step away from to easily control that. And then that just becomes another note that their instrument makes. So they can control it and do stuff with it. It just becomes another note to accent things. So not always an annoyance, but that's what machines do on their own. Machines take in input, do some sort of processing on it, and send out output. I'll draw some little arrows on those input output things. That's our normal process. But if we need to repeat things, the natural way to make that, there's nothing in the machine to naturally repeat on its own. So repetition has to come from taking our output and sending that back to our input, usually with slight modifications. So I'll stick something along the way so that it's not an infinite loop sort of thing. There's a modification, so there's eventually a stopping point. That's very important. But when we control that feedback loop in order to do things, in programming, we refer to that as recursion. Well, really, there's a couple of things we need to do it, but that's what machines do naturally. They have feedback loops. So when we can control those feedback loops to repeat instruction calls, we have recursion under certain conditions, under specific conditions. There are three criteria we have to meet in order to actually be recursion. I'm going to erase these pictures if that's okay. Well, this picture is just scribbles by this point, so hopefully that makes sense. But I know everybody's experienced audio feedback. I just was able to actually do a sample of it for a Zoom call. And this is our basic process. Input processes to output, then that output becomes the next input. And that will keep going until we're done repeating. And that's our natural repetition structure for machines. However, it can be a little difficult to work with because we have to meet three criteria. Our problem must reduce to a base case. Actually, I don't want to write that one first. The problem must reduce to a smaller version of itself. on there. Our second criteria is there must be an eventual base case. This reducing must eventually stop. So it has to be a situation that it can't be reduced forever. Have to eventually hit a stopping point. The normal terminology for that is we hit a base case. And the third one is our solution has to refer to itself. Solution to problem must refer to itself. Let me know. So some cases lend themselves to this very nicely. The standard example to start out with is factorials. Okay, 5 factorial, which if you haven't seen that in math class, we take the number and multiply it by everything smaller. So 5 times 4 times 3 times 2 times 1, and really the times 1 there at the end is just because it doesn't make any sense to stop our pattern at 2. If we're going to walk down, we walk all the way down to 1, and times 1 doesn't change anything. But if we look at that next part, 4 times 3 times 2 times 1, that's actually 4 factorial. So 5 factorial could also be viewed as 5 times 4 factorial. And 4 factorial would do the same thing, 4 times 3 times 2 times 1. But 3 times 2 times 1 is 3 factorial. So we get 4 times 3 factorial. And 3 factorial is, well, 3 times 2 factorial. I think you see where that's going. That's a standard introduction to recursion because it fits our criteria on its own. The problem reduces to a smaller version of itself. 5 factorial is 5 times 4 factorial. Or for any arbitrary number, I'll call it n. We could say n is equal to n times n minus 1 factorial. And just keep going until we get all the way down. So it reduces to a smaller version of itself. We're going down. So somewhere down here, there has to be a 0. There is an eventual stopping point. There's a definition in there. Definition 0 factorial is defined to be 1. That way we can walk down all the way to 0 because that makes even more sense than walking down just to 1. We walk down until we hit our natural stopping point, but there's a natural stopping point. And the solution refers to itself. To solve a factorial, we multiply by a smaller factorial. So it's a natural recursive thing. That's the situation we have to have in order to use recursion to solve things with programming. Works great for factorials, make a nice straightforward example, but not all our problems fit those criteria. So sometimes what we have to do is modify our problem. And sometimes that's not even enough. Sometimes modifying our problem we can't even modify our problem to fit those criteria. Sometimes we have to solve a different problem, a related problem, and then use that related solution to come back and figure out what our original problem was. It can be very difficult, something that can be a little tricky to think about and complicated, very much in the realm of working working under mindsets of how machines need to actually physically operate. So sometimes even getting back to the electrical engineering level. Kind of complicated. So then around in the early 60s, it was very, very complicated and computers were growing, and in the early 1960s, loops were invented, which is a structure to make things easy. Y'all know what loops are. We use our selection structures, those normal condition things. CPUs do 2's complement, so we can subtract numbers, and if we subtract two numbers and we get a 0, they're equal. It's 2's complement, so we always have an extra bit left over. So we subtract a number, we look at that extra bit, and that extra bit is either going to tell us whether we have a positive or negative number. And that tells us whether the first number or second number was larger when we subtracted them. So there's our 3 comparisons. Or for those who are continuing further, when you get to assembly language, that's your jump on carry and jump on 0. That's what we say when we mean loops, which gets into assembly language and kind of drifts away from what we're studying, but it's made to be easier for a human. But there's a trade-off. This is what a machine does on its own. So it's better for the machine. It's faster, basically. I believe everybody has seen some recursion before at this point. I know those of you all have had me before have seen some, so we're just going to kind of look at a quick example. But we look at our problem, and then we write sort of a generic version, a function that we can call that addresses that problem. And then we have that function, one of the instructions in that function is to call itself, so that it keeps running over and over and over again until we eventually get to our solution. Factorials are a great example. So you can just write a function that finds the factorial. It's a really easy one. I'll write it up here. That's a standard example. It's really easy. That's not the one I was going to do here. So define a function called factorial. I'm on the board still, yeah. It's going to take in some number. We just check and see if we're at the base case. So first thing we always do in a recursive call, a recursive function, is check our base case. So if n is equal to a 1, I'll say less than or equal to 1, we return n. If it's not, well, we'll ask for another factorial. We'll return n times the factorial of n minus 1. So if we're at our base case, just return that number. If we're not at our base case, do this over and over and over again until we get down to that base case. A straightforward one. That's a common example. I know for certain three of y'all on this here tonight have seen me go over that in class before. So I'll skip ahead to a more interesting example. And yeah, the rest of the roster tonight is something I know is really good at programming, so I'm not worried about skipping over the easy examples. So we'll look at something more interesting. And that makes this a lot easier, because our base case is when we get to the end of the directory. Right? That's an easy base case to find. We just check and see if there's anything else. Then we only need one if statement to check instead of 3 like we need in the loop, because of that. What's actually going on in assembly language? We subtract the 2 values to get, and then we have either, after subtracting, we either have a positive or negative or 0. If it's 0, they're equal. Positive or negative, that tells us which one was bigger than the other, and which would be a binary state, right? Positive or negative is a binary state, or 0, and then we have 2 flags, and all of our assembly languages have jump on 0 and jump on carry. So that's what's going on in the loop. But when we jump to directory structures, we kind of have to check all of those things, or we risk missing a case. So it's almost like we're using assembly language to put our loop together, or we risk missing some stuff, which defeats the whole purpose of a structure whose sole purpose is to make it easier for a human to work with, right? Because assembly language isn't the easiest thing to work with. So if we have to think like we're working in assembly language, to work in a high level language, it makes the loop pointless. So recursion is a great version for this. But yeah, I'll kind of do something like that and print stuff out. Printing's a nice clean version for class examples. Oh, I'll do the same thing. So from from OS, import everything, and from os.path, import everything. So this is what we just looked at it a moment ago. Oh, whoops, I'm not sharing my screen, sorry. Okay, with the screen share going, this is what we looked at a moment ago. This is what I almost always do. I don't stop and think about which methods I need. I had to specifically look that up this afternoon because I couldn't remember which ones went with which one of those modules. I almost always do it this way. It's a common thing. So I'll look at the directory. I'll look at the same thing again. So the base path we want to look at is that directory. So like C, the users folder, this particular user account, and the documents folder to work. And then I'll just, I'll put that in a list. Stuff is going to be a list. So what do we need to do for a list? Same thing we just saw, right? So for folder in folder in list directory of the path we're looking at. So we'll look at all of them and just check if that's a directory. If is directory join path and folder. We'll add it to the list. We've seen that a couple times, right? One of the biggest advantages of Python is we have those list comprehensions and generators and all the little things like that, where we can handle all of that in one line of code. About half of what we were doing over here. And now I'm just going to go through this recursively. I'll just do a recursive call on this because, well, it's coming on the time I like to end. And then there's one more point I want to look at for this. So we might not get to that other exception handling thing that I wanted to show. But we can, this class stretches out for 16 weeks, so we can look at that other exception handling and actually fix the problem on Thursday. Because fixing a problem does take a moment. So for recursion, we need a function. We need a solution that we can call over and over again. A function that we can just keep asking for again. For a simple example, I'm just going to print this out forwards and backwards, maybe. So we'll have this function that takes in a list. And if the length of our list is not equal to 0, yeah, I'll do this. Or I can do equal 0. If it's equal, why does that keep running? Keep bumping a button and I'm not sure which button is just making that run. So if the length of our list is 0, we're done recursively calling it, right? That's our base case. We're looping through the list. So this is alternative to looping through a list. One item at a time, we'll just print them out. If we get all the way to our base case, we'll just return it. We're like, okay, that's done. We'll just return emptiness at that point. But if we're not at our base case, Then we'll print out the next item in the list and call that method with one less item. Does that code make sense? So, and this is the sort of the epitome of why computers work in a stack. So, where's my little pen? Oops, that's not my pen. That was stuff there. There's the pen. Clear that. Try to draw the thing I was actually trying to draw. So one of our standard diagrams for representing things, we have our stack heap diagram. Stack over here and heap. Stack representing the code we feed in, the instructions we feed in, and the heap representing dynamic memory. So when we call this, we have F with that full list. We call that function with the full list. And then that function, in order to run that, we haven't got to the empty list. So that function is going to call the thing again. Right? It's not the end of the list, so it's going to print something out and then call that again. So it hasn't actually got to the end of the functions. It has to wait till that call comes back before that first function ends and we can pop it off the stack. Then we call that function again. Hopefully the abbreviation there in the picture is okay. Sorry, it's really hard to draw with the mouse pad. So we call that same one again. But if it's not the end of the list, it's going to print something out and call the function again. And our stack just keeps getting taller and taller and taller because we haven't actually come back from anything yet. We're still in the middle of running a function when we call the next one. But eventually we'll get to the end of the list and then we'll get a return statement. And at that point, we'll just sail right back down to the bottom of that stack because then everything's finished. There's nothing to do when we get back. So hopefully from that little stack heap diagram, you notice that kind of looks like it's the perfect thing to go in that diagram that we normally use. The normal computer science, software development, software engineering, maybe some in IT support, but the normal thing we use to represent what's actually happening inside a machine, our normal stack heap diagram. The stack looks like a perfect thing for it. And it is. It's what the machine does naturally. But you'll also notice that it gets a little resource intensive. Close this, let me run this. Uh-oh. Folder. There's not undefined that. What about my example? Folder and list directory path. I don't see where I made a typo there. Name folder is not defined. I don't see a typo, so I'm going to retype that. So the thing I want is, I want the folder we're looking at then I'm going to loop through some sort of iterative structure. Well, directory path is an iterative structure. It's going to say for folder in list directory of that path if it is a directory to when we join the path with that folder. Okay, I must have made a typo. I was not seeing it, and y'all have probably encountered that before by now. But sometimes we just don't see the typo when we look at the line. If you know what line it's on and you're not seeing the typo, the human brain has a tendency to fill in gaps. Sometimes it will do that because our brains know what the code we wrote is supposed to say. So it will do that intuitive thing that the human brain does to prevent sensory overload and just not pay attention to the entire environment and fill in gaps. And it will do that with the code we're looking at. We will see the correct code, but there's actually a typo in the line. So sometimes the best thing to do is, especially if you know what line it's on, delete that line and retype it. So now I can call that method, I'll call the forward method and pass in that variable stuff. Well, that should be more than one item long. Oh. Sorry, I was thinking about backwards. I was going to do backwards here in a minute. Actually, that might have been a typo. There's still a 0 in there. So we print the first element. Hopefully that you looked at that and it wasn't making any sense. What we're supposed to do is print the first element, and then we pass on from element 2 on. So print the first element and then pass the rest of the list on through the second index on. There we go. So I printed it out. Probably seems a lot like a loop at that point. We do a similar thing for backwards. I'll just copy and paste and make a backward thing. That way I don't make more typos, but backwards would be the same thing. Our base case for a folder is when there's no more things in that list to look at. And then we can just return, but otherwise we'll print out our last index and then pass on everything before that index. Hopefully that makes sense, seeing both of them there. Okay, we print out the first index and then pass the rest of the list. Or we print out the last index and pass on the rest of the list. So prints it forward, prints it backwards. Maybe a couple blank print statements in between there. Space them out. That'll work. And so I think everybody's seen recursion before. You can see that to set up recursion for directory structures is a very straightforward process. It so happened they fell together, so I wanted to do something better than our normal example that fits the case perfectly. Something that takes a little more thought, but it gives us a way to loop through things. So, but like with that forward method, we already had a way to loop through things, right? Print recursive, then I'll print a couple empty lines. But don't we have stuff like this? So for S in stuff, print S. Looks like about the same. That looks like we just made another way to do that. But again, it's back to that loops were put on there to make things easier for humans, not for the machine. Oh, print recursive, print for loop. So we can see what we're looking at. Looks like it did the same thing, but now that thing we've been kind of trying to work in this week. We're in the second half of our semester now. Maybe we could do a check to see what is going on with it. And earlier today, I kept getting a weird error. So I was only getting an actual result every third time. And it was very, very obvious. You'll see what I mean, why it's obviously not the right result. But what's a good thing to check? We can check time. So let's check and see how long it takes those two things to run. That's a good telemetry, a measurement to take of our code to see if one's better than the other. So I'm going to import the default time module. And right before that recursive call runs, I'll take a measurement of the time. So like current is time dot time underscore ns is a function that gives us the current nanoseconds as far as our computer does. So we'll grab right before that function runs, we can grab the current measurement of nanoseconds. Then after that function runs, well, we can do the same thing. So duration is so hopefully everybody's seen this in a math class when we need to do a code or when we need to find a difference. Delta T is how it's normally written in math or science classes, a time interval. We always do new minus old. So we'll take another measurement of nanoseconds. So time underscore ns gives us the new measurement, and we can subtract off the old measurement to find out what that difference is. Then we can print that number out. Print time plus cast duration into a string. So nothing too fancy. We take a measurement and then just echo that back because we're the only ones that need to see that measurement. It's for comparisons. As we're trying to figure out what would improve our code. I'll just copy and paste those lines down and do the same thing after running the for loop. So after we do a for loop, we'll take a duration. And I'll do this before. And you want to be consistent when you're taking measurements, right? Like we're measuring nanoseconds, and printing that label before it does take an amount of time. Seems instant compared to human timescales, but if we're measuring nanoseconds, it is a measurable amount of time. So we want to be consistent. So the first one measurement was taken after our label. So down here we'll take a measurement after our label because those labels are not the same. So not only are they going to take an amount of time, those labels are going to take a different amount of time. So when you go to measure stuff and make your comparisons, you want to keep things like that in mind. And when I was getting ready, I was getting a really strange thing happening. I'm going to take out any empty spaces, try to make it as consistent as I can between them. So all we do is take a measurement, do that, pass through our loop. We have two ways of walking through our loop. And then take another measurement, the difference of those measurements, and print that out. So it's consistent on both. So it should give us some information. So I'll come over here and hit Control L to clear that and run this. Oh, did I make a typo? Yeah. Fix the typos. I'm guessing after several programming classes, you all are quite familiar with that point. Oh, yeah, this is the weird issue I was getting before. We can see it there on the second loop, it says time to 0. And that did not take 0 nanoseconds to do. It was only giving me something that was reasonable numbers every third time. It says both of them took 0 nanoseconds. I know that cannot be accurate. Okay, so the second time it gave me some nanoseconds on one of them, but not the other. I haven't done telemetry in Python for a while, so I might have missed like a setup or something. By the time it gave on the first one, but not the second one. Back to 0. 0 again, but if we run instructions, there's no way that it's doing those instructions to 0 seconds. There we go. I'm not sure what happened there. I might try a couple things over the next 3 minutes. Was the time I wanted to have, but oh no, it didn't give it to us. I guess we'll have to look at it. So we can see that the time it did measure that, because we know for certain that it did not take 0 nanoseconds to run a loop of Python, right? It's very, very quick, but it's not 0 nanoseconds. A nanosecond, we think about how small it is, right? There's millis is 1,000th of a second. The nanos, the next 3 digits down, so that's 1,000,000th of a second. We did not do that. We did not run through a loop in less than 1,000,000th of a second. So that 0 doesn't make any sense. But we can see 868,100. I'll write that down somewhere. So loop is 868,100. And recursion gives us a 0. Gives us a 0. There we go. When we get a non-zero number there, we get like 174,600. Those are both nanoseconds, right? That's going to have to get really big before a human notices the difference. But sometimes we are working with really big problems. There's still plenty of really big things we can do. And you see the loop was a whole lot longer. And if you think about it, it took more code for us to put that together, to put together that recursive call, which is what a machine does naturally. So we should anticipate that that's better for, there's going to be some advantages if we do what the machine does naturally. So put some of that work on the programmer. And we got a serious increase in time. Maybe I need to initialize that somewhere up here. Let me see if this works. Initial time is time in nanoseconds. Maybe that would fix that 0 issue. Nope, still doing a 0. I run it a couple times, maybe I'll get something that has numbers on both of them. There's a number there. Oh, that time they're really close. Looks like the first one, the recursive call was quicker that time. So we're getting inconsistent numbers back, right? The recursion call is usually going to be quicker because it's better for the machine. It should make sense. However, the trade-off for that is using recursion can be very resource intensive. When I started drawing the quick sketch of the stack heap diagram there, you saw it was filling up a stack very quickly and nothing was getting cleared out of the stack. So it it will fill up our RAM. It uses our resources. It uses a lot of our RAM very quickly. So recursion was a lot better before the days of multi-threading. Because on a modern computer, the operating system is probably multi-threading a lot of stuff automatically. So it's going to try to do more than one thing at a time. Which, if we filled up the entire RAM chip or most of the RAM chip with the repeated calls to a function in recursion, that's going to affect other things the computer's trying to multi-thread. So that's the trade-off for it, but it is usually considerably faster. This time where we're seeing both, it's showing that the recursion was slower. And I have no idea why this number is doing this. So now those numbers are completely switched around. So that's something that something's going wrong when I'm with this measurement. I was actually looking for ticks, but I think that might be MicroPython. Yeah, it doesn't know what ticks is. That's MicroPython like we would use on an embedded system. Oh, okay. So that didn't help. And I'm not sure why it's giving a 0, because we know it does not take 0 seconds to do that. Maybe it has something to do with this. Oh, over here, we'll explore if I clear that. Run that. Oh, there we go. Oh, that's showing the recursion taking a lot longer. And you know what? I bet that is Zoom trying to multi-thread stuff. Because recursion is very resource intensive, but so is Zoom. So while we're doing something very resource intensive, that's going to affect. So after class, when not on a Zoom call, run that code by itself. And for some reason, I have no idea what that 0 is about, but we know that is obviously wrong. Because it does not take 0 nanoseconds to run an instruction of computer code. It does take a certain amount of nanoseconds. But typically recursion will be much, much faster. The main takeaway though, obviously the loops are going to be much easier to write. The main takeaway is just that idea of taking measurements. Another step on that. As you put your code together, take some measurements. It might be just because it's doing just one thing, but when I'm grading for the rest of the semester, go ahead and expect that I'm going to do something like that. Already, right? So I won't hit run. I will actually call your code. So I'll say like, I'll do that right there. So I'll just copy it from here. Instead of hitting a run button in your code, I will call it something more like this. Execute, open, I don't know, homework.py, whatever we're calling it, .read. And I will actually run your homework assignments that way and take measurements on it and stuff. It might make some changes and stuff, so keep that in mind. As we're moving forward, that's the sort of stuff we're looking at. Not just did we accomplish the task that we set out to, but how well did we accomplish the task? So we've seen the two things there. The time's our second one, so you can just take that measurement, or you can look up how to measure time in Python. There's more than one way. What I was thinking of when I first went to that is actually something from MicroPython, which apparently isn't in regular Python. So do I have view time? I do. Let's see if ticks works. Nope, no, you don't. So there's better ways to do it than that. But that'll hopefully get us a start without spending a lot of time. That gives us a measurement of nanoseconds. So run a few lines of code, see how long it takes. And if you have more than one idea on ways to do something, take those measurements, see which one's better. The Zoom call is definitely affecting this because recursion is very resource intensive, so it needs a lot of the RAM chip. But if that was the only thing running, there wasn't a Zoom call trying to go at the same time as that recursive call, the recursion would be a lot quicker. So check that code after the Zoom call, and you'll see a big difference from the numbers we're getting here. Actually, something more like this. For a simple thing like this, it should be about 6 times bigger. But it's much faster, and sometimes that's what we want. We need to buy back that extra speed. But as always, there's a trade-off. It takes more code from on our part to do it, but the basic idea of recursion there, that was the main thing I wanted to talk about. These 3 criteria, it's natural to the machine. So it's going to be, other than how we keep stacking stuff up in RAM, so it's going to use a whole lot of the RAM chip. It's quicker. Controlling feedback to repeat instructions. And some of our languages do not have loops. We do still use some languages that were written back in the 50s before loops were created or loops were invented. And if you don't have a loop access to a loop in the language you're working in, or you want to try different versions, recursion is always a good option because it's going to be very, very fast, and you need to meet these 3 criteria. You have to have a problem that we're reduced to a smaller version of itself, or can be somehow modified into fitting that format. And it has to eventually stop at a base case. And then the call to the function should be obvious at that point. That was a lot of content in the last couple modules, right? Lots of writing files. And tonight we saw working with the operating system, like working with the folders so we can organize those files nicely and look for them if we lose track of them or that sort of thing. So one other thing I wanted to do with file writing, which I guess will be done on Thursday, which is actually fix a problem. The plan is when our software depends on a file that we have to read in, what happens when that file is not there? The general version of exception handling that we see in textbooks and tutorials, which are always kept short and to the point, that would be a problem. The program would crash, it would no longer keep running. And that needs to be our goal, is we want to keep that program running if at all possible. So I have an example in mind to see a case of that and sort of how we approach that. But a whole lot of material in last week. Hopefully it'll be useful things. Kind of an important thing, something we want from all of our software to do. And then here at the end, recursion is natural to machine. So some of our languages don't even have loops. So we have to go with recursion. And if we can deal with the resource intensiveness of it, like if it's not going to use the entire RAM chip at once, we get a lot more speed out of it. Otherwise, I guess that'll be it for this evening, unless anybody had any questions about stuff. Question. Okay, I assume the silence means no questions. If y'all have any, let me know. I'm always happy to help. Otherwise, you have a great evening, and I'll see you Tuesday. And, okay. I'll look at that real quick, after the video. Or stop the video. So I'll see you on Thursday. I'll stop the video and look at that.